All right, we have Kaustubh Banerjee. He's electrical engineer, systems protection analyst, and Brittany Chapman, engineering manager, protection and control design, both PEs. Hello. Kaustubh, you give a little introduction about yourself, please.
Sure. Hello, everyone. I'm Kaustubh Banerjee. I am an electrical engineer at Commonwealth Associates, and I have been with this company for more than 8 years. I have extensive experience performing relay settings and relay coordination projects for various utility clients. And I have also applied NERC, PRC, and MOD standards to meet compliance for our various clients. Recently, I got involved in IEC 61850 enable substation projects, and I have been setting relays which are 61850 enabled. So I'm really excited to talk about this subject today in this webinar, and I hope that everyone attending this webinar can get something out of it. Thank you.
Sure. So I am Brittany Chapman. I am an engineering manager for Commonwealth Associates for Protection and Design. I have my Bachelor's of Science from UCF here in Central Florida. I am in Orlando, Florida. I have 10 years of experience working for equipment manufacturers and in the consulting industry, all the way from generation to distribution. I really enjoy this work. I enjoy the challenge of it, and I love working at Commonwealth. Very excited to present this topic to you all today, and look forward to the rest of it.
All right, thank you, Brittany. All right, I will be leaving you all here in the capable hands of Brittany and Kaustubh. I'll be fielding any chats and picking up your questions for the Q&A later, and we will see you on the other side there. All right, Brittany, take it away.
Thank you, Del. I'm going to go ahead and turn off my camera just to make sure that we have good streaming quality for anyone who may have low bandwidth. So I'm going to go ahead and turn that off now. And we will move on. So this is the agenda for today. So first things first, a safety moment. Just make sure that you are in a safe location while listening to or watching this webinar. If you're at home or in an office environment and you have to get up and take a break, or after the webinar when you get up to take a break, make sure to take it easy when you get up. Don't get lightheaded. Make sure that there's nothing around your feet that you can trip over. If you have to go downstairs like I do for some water afterwards, make sure to be careful going down the stairs, and just keep awareness around you at all times. Make sure that you are safe. The next thing we're going to go through is a Commonwealth overview. This should be pretty brief, just to go over some of our qualifications and the qualifications that Kaustubh and I have. And then we will get into the bulk of the presentation, talking about communication-based versus traditional PNC design, a history and an overview of how that happened and how it's evolved. We'll dig hard into the IEC 61850 standards, and then we'll be covering some very high-level implementation examples before we go to Q&A. Implementation, as you all know, in engineering, there are multiple ways to do the same thing. So our implementation examples are going to be pretty high level, but hopefully they will be informative and give you some ideas about how you can take this technology and apply it where you are. So first things first, Commonwealth overview. So we've been innovating in electric power since 1888, and that is not a typo. 1888 is the real year. In our current form, we've been employee owned and managed for 30+ years. We were awarded a top 10 design firm by EC&M magazine, top 500 design firm by ENR, and we have 7+ years experience providing 61850 engineering services for our clients. Industry leadership for Kaustubh and I, we hold several different positions and memberships within PSCCC and PSRC. So we love to give back to our engineering community. I am an officer in the PSCCC task force for P13, IEC 61850 for beginners and a member of the PSCCC P0 Committee for Protocols. And CoStub is a member of PSRC C45 Working Group for Short Circuit Monitoring of Systems with Inverter-Based Resources. So we truly love giving back to the engineering community, and we're very proud of our industry leadership and the way that we give back to this industry. Commonwealth locations. So we have office locations in, I believe, 5 states now. One state actually has 2 office locations in it. That's Texas. It has Austin and Houston in Texas. We are licensed in 49 states out of 50 and have staffing all over the country. So we're not limited to just where our office locations are. We have a very broad base of individuals and professionals available to do work. So we're very proud of how much of this map we are able to cover and our qualifications serving the US. Okay, so our first poll question is coming up. Just to get a feel for our audience and where you might be with 61850 or communication-based protection. So our question is, what experience have you had with communication-based protection, such as IEC 61850? I know of it, but have not used it. I understand it, but have not put it into practice. I have worked with it, but am still refining using it, or I have implemented it and have refined standards. And we'll give you all a few minutes to go ahead and answer that question, and we'll look at the results when it's complete.
Thanks, Brittany. This is Del again. We've got, let's see, about 60% of attendees have voted. About 30 seconds, so we'll wait a few more seconds before we close up the poll and get some results. Okay, with about 77% of participation. Oh, 79, there we go. All right, we'll get this out here. Some results for us. In first place, 65% of those who took part in the poll, I know of it, but I have not used it. 19%, I understand it, but I have not put it into practice. 12%, I have worked with it, but I am still refining the process. And 4%, I have implemented it, but have refined standard in usage. So very heavy on those who know of it, but have not used it. Thank you all.
Yes, thank you all for your input. Now, at this point, I'm going to turn the presentation over to CoStub to start us off with a brief history.
Thank you, Brittany. Yeah, so looks like a lot of our audience know about 61850 but have not used it. So I guess the next several slides will dive into the theory of 61850 and hopefully we'll give a refresher on the theory. So before I start talking about 61850 in earnest, let's see how 61850 came into being in the first place. Since early times, power system protection has been dominated by electromechanical relays. These relays function using a magnetic field produced by an electromagnetic coil when a control signal is applied to it. These relays did not communicate with each other or with the control center to provide data points like status information. However, in the 1960s, data acquisition system became viable, which could collect measurement data from substations. But these systems were still limited by low bandwidth. Now, in 1980s, multifunction solid-state relays were introduced. These relays could perform both protection and control functions as well as monitoring functions as well. So these types of relays are known as intelligent electronic devices, or IEDs. A single IED is able to collect thousands of analog and digital data points. Multifunction IEDs led to the realization that standardization for common protocols, message structures, and common methods of database access were needed. So in 1986, APRI introduced 2949 project called the Integration of Utility Communication System, or the UCA protocol. Those protocols were released in 1991. Now, IEC got involved and commissioned 61850 set of standard in 1995, which was the output of the Technical Committee 57 Working Group 11, 12, and 13. So desire for one standard led to the North American entities providing specification as a starting point for this work in 1998, and thus the formal work to develop the combined standard began. And this culminated in 2002-2004 with the release of a suite of 61850 standard in its first edition. So the suite of standards in IEC 61850 not only define the communication protocols for IEDs in the substation, but also describe the modeling, organization of data from the IEDs and its mapping to the communication protocols for the power system devices. The IEC 61850 standard was a response to the growing need for higher and deeper level of automation in electrical grids. It had become clear that future demands could not be met with technological limits of serial protocol like Modbus. Next slide, please. Okay, so let's go over briefly go over the contents of the suite of standards which make up the 61850. The stated scope of 61850 was communication within the substation. Various aspects of the substation communication network are defined in various parts of the standard. Like, for example, the general requirements of the communication system and project management, and other communication requirements are mentioned in parts 3, 4, and 5 of the standard. These identify the general and specific functional requirements for communication in a substation. These parts provide guidelines for reliability, availability, security, data integrity of the communication system that are used for monitoring and control of processes within the substation. Now, the standard also talks about a substation configuration language, SCL, that is based on the XML language to describe the configuration of the various 61850 enabled devices on the network. One of the major features of 61850 is abstracting the definition of the various data items and services that it can provide. This makes the data items and objects independent of any underlying protocols. I will describe more about the abstraction and data modeling on my next several slides. So the standard also describes mapping of these abstract data objects and services to real-world protocol stacks like manufacturing messaging specification, or MMS. And it also describes mapping of something called sampled values protocol onto the Ethernet data frame. These are all I will be talking about in my next slides. So all these protocols and data abstraction on the logical device requires significant amount of configuration in order to put all the pieces together and have them work. So the SCL files facilitates this since it allows the formal description of the relations between the substation automation system in the IDs and the substation equipment. Finally, part 10 defines the testing methodology in order to determine conformance with protocol definitions and constraints. Next slide. So let us talk more about data abstraction and data modeling in the 61850 standard and how it comes about. So this standard is unique in that it provides a comprehensive model for how power system devices should organize data in a manner that is consistent with all types of and brands of devices. So implementation of 61850 is not dependent on any particular type of brand of device being used. So you can have relays or IDs of a particular brand, and then you can also have remote input-output devices of different manufacturer, all in the same framework of 61850. So this is 61850's one of the greatest advantage. The way data is structured and organized in devices connected to the 61850 network is called device modeling. So the data can be anything from metering signal data to trip signal data. So these data items and services are independent of any underlying communication protocols. The 61850 have guidelines to map all these abstract data models and services to specific protocol stack like MMS or Ethernet data frame. Next slide, please. Okay, so let's dive into the 61850 device modeling. So the device model begins with an actual physical device. The device is a unit, the physical device is a unit which connects to the network like an ID or relays. So the physical device can be found on the network by its network address. Now, each physical device may contain one or more logical device inside it. Thus, in this way, it acts as a data concentrator. So now, zooming in further, we can see that each logical device contain one or more logical nodes. What is a logical node, you may ask? Well, it's a grouping of data and associated services that is logically related to some power system functions. The naming of the logical node depends on the type of function being performed. For example, the name of the logical node which performs metering and measurement function begins with letter M. Logical nodes for protection function start with the letter P. So you get the idea, right? Now, each logical node may contain one or more data elements. The name of these data elements are determined by 61850 standard and are functionally related to the power system purpose. Again, diving into an example, suppose you have a circuit breaker in the yard and you want to model that circuit breaker and its information in an IED. And that circuit breaker can be modeled as a logical node in that IED, whose name will start with the letter X according to the standard. So in this case, it would be the XCBR logical node as shown in the diagram. That node will have multiple data elements. One of the data elements will be about the mode of operation of the breaker, whether it's in remote or local mode of operation. Another data element may store the operation count of the circuit breaker. Similarly, there would be a switch position data or data for open, close, block commands. Now, these data elements conform to something called the common data class, which is detailed in part 7 of the standard. The common data class describes how the data should be structured in the logical node. So it describes the type and structure of the data. The common data class will again have data attribute name, attribute type, and its functional constraint. So the bottom diagram in this slide shows you the data object that comes about by applying this device modeling. And this data object has been mapped to MMS protocol stack. So I will talk more about this data object and what it means in my upcoming slides. Next slide, please. Now, here are some examples of the naming conventions of for logical nodes. As mentioned in my last slide, a logical node would be a named grouping of data and associated services that is logically related to some power system functions. Like, for example, there can be a logical node for representing the metering and voltage measurement data from a transformer. So in that case, since it's a measurement related data, the name of that logical node will start with the letter M for metering and measurement. Similarly, like if the data elements contain the protection related information, then the logical node for that will start with the letter P. And if you're modeling a circuit breaker, which is a type of switchgear, then the logical node for that circuit breaker, which will handle the information for that circuit breaker, will start with the letter X, which is XCBR in this. You can see from the last column in this table. So yeah, next slide, please. So let's look into an example of what is contained inside the logical node or its description. So the information in this table is for the XCBR logical node, or the switchgear logical node, which we have seen that it corresponds to circuit breaker modeling. So you can see that this logical node is made up of multiple data points or data elements. For example, there's a data element called LOC, which is for providing information on the mode of operation of the breaker, whether it's in local operation. Local operation means operation without substation automation communication, or due to hardwired direct control operation. So this LOC data element will have a data attribute type, which will correspond to one of the common data class. Now, the common data class, basically tells you the structure and type of the corresponding data element. So to recap, the LOC data, or the logical operation data is present. That means that the breaker is either in local operation or the remote operation. Similarly, you have other data elements related to circuit breaker function, like the operation counter, the switch position data element, or the circuit breaker operating capability data element, which stores the information about the circuit breaker operating capability. So each logical node will have this kind of set of data elements, and it will show you what data elements makes up that logical element. Next slide, please. Okay, so in front of our screens, we have an example of the common data class that I was talking about. This common data class, this particular example is of the single point status common data class. So the common data class can be thought of as a template. So this template will contain various further information given by the data attribute of the common data class. The data attribute will have the attribute type and also functional constraint. So let's go back to our previous example of a circuit breaker logical node. In that logical node, there was a local operation data element, which tells you about the mode of operation of the breaker, whether it's local or remote. Now, the local operation data element is a single point status type of data element. Now, from this table, we can see that the single point status class has a status value field, a quality check field, and a timestamp field. And these fields provide status related information, right? So hence, under the functional constraint column, you see that it has the identifier ST, which means that these are status type of data. So the local operation data element in the circuit breaker logical node will contain this, will have information about the status value, the quality check, and the timestamp, among other things. Of course, the local operation data element will also have other data from the single point status data class, like enable data or CDC data, which are extended name, functional constraint, and all that. Next slide, please. So this slide shows how the device modeling that we have seen so far builds up to the abstract data object, which can be accessed and transmitted in the 61850 network. So this is an example of a data object structure which has been mapped to MMS object protocol. So suppose there's a physical device, an IED, which has a logical device in it, which is being modeled by relay 1 in this diagram. Now relay 1, suppose relay 1 contains a logical node which models a circuit breaker in the yard, which is given by XCBR1 identifier. So that's the name of the logical node for the circuit breaker. Now suppose for that circuit breaker, we want to know whether the circuit breaker is in local mode of operation or remote mode of operation, then we need to look at the data element, which is given by the LOC identifier. So the LOC data element will have a data attribute, which is the status value, which will provide you the actual information on whether the circuit breaker is in local or remote mode of operation. And the functional constraint, which is given by the ST identifier, tells you that this status value is a status kind of information. So if you read this word together as a whole, then you will get the complete information on the mode of operation of the circuit breaker in that substation. And this has been modeled on, as I said, on the MMS protocol. So this is how 67850 abstracts the data and builds up a data object that can be used in the network. Next slide, please. So as we move towards the digital substation implementation, the ability to digitize voltage and current signals from the CTs and PTs, and then transmitting the resulting sampled values back to the substation becomes a necessity. Further, the ability to remotely acquire status information from remote input-output devices and providing output controls for the power system equipment like breakers in the switchyard is also desirable. So 61850 addresses this with the help of sample valued services and implementation of something called the process bus. So what is a process bus? Process bus is where the process level information of the substation, such as voltage and current signals, status and control information, are transmitted. The digitization of these analog power system signals are performed by the merging units, as you can see in the diagram. And these merging units are out in the switchyard near the power system equipment. So these units sample the analog signals at an agreed time synchronized rate, and then any IEDs in the substation can input data from multiple merging units. So imagine that one of the IEDs in the diagram is a bus differential relay protecting the power system bus, which has multiple line exits. So each of these line exits can have a merging unit which digitizes the CT signal from that line. So the bus differential IED can subscribe to the current signals from all these MUs or merging units on the line exits in order to receive data on the line currents and perform differential calculation to protect the bus. So in this way, digitized data from the merging units can be passed to the subscribing IEDs using the process bus, which is implemented on an Ethernet data frame. Now, what is the protocol for collecting and transferring all this digitized data? So it's the sample values protocol or data service. And 61850 actually defines two different sample values data collection and transfer protocol. Part 9.1 of the standard defines a unidirectional multi-drop point-to-point fixed link carrying fixed data set. So this data set is carried over a serial link, while the other protocol, which is defined in part 9.2, is a publisher to multiple subscriber model carrying configurable data set or user-defined data set. So this is a more generalized implementation of sampled values protocol. Next slide, please. Now, similar to a process bus, there's something called station bus. Station bus exists at a substation level, and primary communications between IEDs, SCADA, and local HMI that might be on the network occurs on this bus. Similar to a process bus, the station bus is implemented by Ethernet link, and they can have 1000 MB Ethernet switches. As mentioned before, the various IEDs in the substation can communicate with the help of the station bus, and the primary protocol, or one of the major protocol that is normally used for the communication, is the GOOSE protocol. The GOOSE stands for Generic Object Oriented Substation Event. This protocol maps directly onto the Ethernet data frame. And GOOSE is a subscriber publisher model type of communication. So in order to explain this model, imagine that IED01 in the diagram is configured to receive a disconnect switch status information. and it has been configured to look into the station bus to see find that disconnect switch status information which is given in dataset 03. Now further, ID 03 over here, its sole job is to ascertain the status of the disconnect switch and put that information on dataset 03 and publish that on the station bus. So once that disconnect switch information has been published on the station bus by ID 03, then ID 01 can get that information since it has been configured to look for that type of information. So in this type of architecture, there's no way for ID 03 to know whether ID 01 has received the disconnect switch status information which was contained in the dataset 03. So the ID 03 needs to keep publishing that information at a synchronized rate onto the station bus so that the data packets are not lost and ID 01 is able to receive that kind of information in this way. So that's the subscriber publisher model. The station bus can also interface with the network gateway where the remote network access is possible. MMS objects and services protocol can be used to access the data on the logical nodes of the IDs of the substation for data read-write purposes. Next slide, please. Okay, so when you put together the process bus and the station bus architecture, then we get something called this 61850 substation model. The diagram on the right shows how it all comes together. You have the merging units that could be located either in the field or in the control house. The merging unit samples the analog signals at the source and publishes it on the process bus. The IDs which are subscribed to the sample signals will receive it from the process bus. The protocol that are normally used on the process bus are the sample values protocol to transfer the digitized power system signals, and also goose protocols to transfer the event messages and protection and control related signals. Then after that, you have the 61850 station bus for communication between the relays, between SCADA and ID, or between local HMI and ID. On the station bus, you can have the also the client server type application interfacing with the network for read-write functionality on the data stored in the logical nodes of the IDs. This together comprises the substation automation system. The process bus and the station bus can be on different networks or by having different Ethernet switches, or they can be on the same network on a common Ethernet data frame. So normally both the process bus and station bus, they are made up of redundant network to minimize the chances of communication failure. One thing to note is that the remote access point in the diagram is a logical location to implement security functions such as encryption and authentication functions. So in this way, the IDs don't have to perform encryption when communicating within the substation, but it can still provide security on all external data transfers. Next slide, please. Okay, so the IDs which connect to the network would need to be configured so that it works on the the 61850 network. Now, configuration tasks would include setting up the relays or IDs to transmit and map the goose messages, subscribe to particular data sets, mapping of data objects to protocols like MMS. So to describe all these configuration, a substation configuration language based on XML is used. The substation configuration language or SCL provides a hierarchy of configuration files that enable multiple levels of the system to be described in an unambiguous and standardized XML format. So this slide shows you the different types of SCL files that exist. So there can be ID capability description or ICD file, which describes the capability and models of the IDs on the network. You can also have the system specification description file or the SSD file, which gives you the overall one-line diagram of the substation. Then there's something called the SCD file, the substation configuration description file, which gives you the configured IDs, description of that IDs in the network. And then the important file is the CID file, which is the configured ID description file, which have configuration information about the ID, about the GUIs mapping data, and also about the data objects for the configured ID. And then the other files are instantiated IID description file, or the IID file, and the system exchange description file, which is the SED file. So if you want to exchange information about the 67050 architecture to a new project, then this kind of files come in handy. Next slide, please. Okay, so we have a poll question here now. What kind of cost savings can be expected between fully 61850 enable substation and a traditional substation design where everything is hardwired? Is it 30%, 42%, 54%, or 72%? We'll give a few minutes for the audience to vote.
Thanks, Costa. We've got folks voting right now. In about 20 seconds, a little over half of our attendees have voted. We'll wait a little bit longer, and we will get to the results here in just a moment.
Great.
We'll do about 10 more seconds. All right, and about 75% of attendees casting their vote. Let's see our result. All right, we have our, okay, let's see, our number one, we've got 54%, and coming in second, 42%, and third is 30%, and the last place is 72%. Now it looks like a single answer to this. So what can you tell us?
Yeah, it looks like the audience is split almost equally between these options. So yeah, before answering this this question, let's go to our next slide, and that is relevant to this question. So before answering the question about the cost saving, a relevant question to ask is, why should we implement communication-based protection in the substation for protecting the power system equipments like transformers, buses, lines? It may seem that the complexity of configuring all the communication architecture to transfer protection and control signals to the correct location reliably may not be worth the effort. So let's look at the other option. What do we have? The other option is to hardwire everything. That is, hardwire the signals from CTs and PTs to the relays in the control house using copper wiring, and also hardwiring all the communication between the IDs in the substation. So as shown in the figure, each signal in a traditional substation, for each signal you would need a wire, and a typical substation can have more than thousands of wire of size 10 or 12 AWG. That is a lot of copper wiring. In contrast, IEC 61850 implementation can get rid of a lot of wiring and streamline maintenance and commissioning. So there was a C-grade case study done by GE in which they showed that implementing 61850 for a substation project led to a cost savings of 54%. So the correct answer is 54%. And looks like majority of our audience got that. And a fully enabled 61850 substation also led to a reduction of more than 1,982 hours of construction and installation work, compared to 3,508 hours of work that you would have to put if the substation was only hardwired, have hardwired signals for protection and control and monitoring functions. So this shows that there's a significant reduction in material and construction cost that can be achieved while implementing 61850. And the 61850 network, in the substation can be implemented using optical fibers, and each fiber can carry hundreds of signals. A typical 61850 enable substation would require only 50 or so optical fibers. So certainly a great cost reduction can be achieved if you migrate a hardwired substation to a fully 61850 enabled substation. So yeah, at this point, I would like Brittany to take over the next slides. Brittany?
Yep. I appreciate it. Can you hear me okay?
Yes, we can hear you.
Wonderful. Okay, so our next slide is going to be another poll. It will be our third and last poll before we dig into some of our implementation examples. So I will go ahead and share that now. We're curious, what has kept you from adopting communication-based protection? Is it a lack of familiarity with implementation, the complexity in configuration or settings? Have you not heard any user feedback? You're not sure of the effectiveness, or some other reason? If you choose the other option, we'd love to see what the reason is. If you could type it in the chat, we'll read out a few of those and see what you all say.
Yes, and Brittany, this is a select all that apply type question. So there may be a few reasons why you have not implemented communication-based protection. So feel free to click more than one if that happens to be your case. Okay, we're about 40 seconds, 45% of our attendees voting. We'll do about 10 more seconds before we get to the results. And as Brittany mentioned, if you did select other, we'd love to hear about that. Maybe put it in the question box and you can ask about that for our Q&A time at the end, or leave it in the comment. Okay, let's wrap this poll up here. Results are in. 51% say lack of familiarity with implementation, followed by other, 41%. 24% say complexity in configuration or settings, and 16% say no user feedback available, not sure of effectiveness. Okay, let's close this and back to you, Brittany.
All right. Thank you, Del. Did we get anything in the question box for the other option?
Not yet, but I will keep an eye on it. We do have some questions coming in, so that question box is open if folks would like to ask their questions on this or anything else coming from the webinar.
Okay. I don't see anything in the chat box, so I'll go ahead and move on. Before I move to the next slide, however, I just want to talk about the implementation details that we're presenting. So as I said in the beginning, with many things, there are multiple ways to implement 61850 into your protection control designs. So we're covering some high-level basics from a hardwired versus network standpoint, and covering some solutions or ideas for documenting those interactions that are now taking place digitally. Before, if you're a protection control person, you pull out a DC schematic. The DC schematic or elementary will tell you a lot of information about how the system is going to operate. One of the things that I've heard personally that has kept individuals from adopting communication-based protection is that they don't have that DC schematic anymore. So we're going to be talking about some solutions for documenting those interactions that are taking place digitally, and hopefully that'll give you a few ideas about how you can implement that where you are. So this implementation example, we're going to start with the design side and then get into the configuration and settings side. So the design side, our presentation is going to take a stepped approach. So we're going to look at how you can slowly implement 61850 from a design perspective to pick and choose parts of your substation or your protection control design that will be impacted, just to control the variables and test out bits and pieces at a time. So here is that stage implementation approach. Our first example is going to be using merging units for the DC signals to the protection relay, but keep the hardwired AC, so our currents and potentials, and relay to relay interaction. So we're talking about breaker failure initiates, things like that. Example 2 is going to show some merging units for DC signals to the protection relay and utilizing a 61850 station bus for that inter-relay connection, so relay to relay. But we are going to keep the hardwired AC to protection relay. So we've certainly seen some of our clients implement this type or style of implementation. And the last example is going to be merging units for AC and DC signals to the protection relay, including a 61850 station bus and process bus. And throughout these examples, we're also going to show a few things based off of offerings from some manufacturers. I am only going to name names a few times, but some manufacturers have more of a point-to-point style of implementation for their merging units to relay connections. So I do want to acknowledge that and acknowledge that those product lines exist. So you'll see a few of those examples in here as well. So first things first, we're going to go to variant A of example 1. So merging units for DC signals to protection relay, hardwired AC. So you can see our currents and our potentials are still hardwired to the relay, as are the relay to relay interactions. So like I said, we're talking about breaker failure initiates or status sharing, that sort of information is still hardwired. So inside the control house, you have still the copper wiring, but from the substation yard into the control house, you're now using fiber. So this allows the user to test out, what is it like having a merging unit, say at a breaker. This is a breaker example. We've seen them used for motor operated switches, that sort of thing as well. So how does this look for those? It's very similar. Of course, with MOSs, you don't have the AC signals necessarily, but you certainly do have quite a few DC signals. So this limits the impact to the design, allowing someone or a company or an entity to test out this one particular function before moving on to implementing more and more pieces of 61850. And we have certainly seen this done for some of our clients who are stepping into the world of 61850. So our variant B of example 1 is very similar, except instead of a point-to-point type of communication between the merging unit and the relay, we now have an Ethernet switch or a switch that is present. So these pieces of information are now published out onto a network. So CoStub earlier was talking about unicast versus multicast. This is the difference in system architecture for what that would look like. So in this type of example, the relays could be pulling information from any merging unit, whereas the previous example, just the relay connected to the merging unit would be receiving the signal, whether that's a breaker status or a trip coil monitor, what have you. Those would be shared in this example. So the switch and the communications equipment is normally kept in the control enclosure. And this would be basically implementing part of a process bus because the AC signals are still hardwired. It's not a full process bus per se. It doesn't use sample values, but this is one example that we have also seen in the 61850 world. All right, let's move on to example 2. So in example 2, like I said, we're removing all of those hardwired communication points or hardwired signals in the control enclosure. So you will see that those have gone away. This uses merging units for the DC signals, 61850 station bus, and hardwired AC to the protection relays. So this looks very similar to our last example, except now we've removed all of those copper connections, and the relays are now also publishing their information on the same network. So this could be like those BFIs or status signals, that sort of thing that I talked about earlier. So this is one such example. If we want to go one step further, this is another example using the point-to-point wiring like I was talking about earlier. So those industry product lines that I'm talking about that have more of a point-to-point architecture between the merging unit and the relay, some are 61850 compatible and some are not. However, that does not mean that you cannot mix them with 61850. I have seen some of those product lines in stations where they are using a manufacturer-specific protocol between the merging unit and the relay, and the relay will communicate 61850 on the station bus. So I've seen this quite a few times now. I think there is a higher level of comfort in this type of implementation because the connections can be traced out a little bit easier. So this is definitely a good stepping stone to go from traditional PNC design to a 61850 based design. So moving on to example 3. So this is the whole shebang. This is the merging units using sampled values. It's the process bus, the station bus. This is the whole thing for 61850. So the merging units in this case are taking the analog signals from your CTs and PTs, of which there can be traditional copper and iron core based versions, or in the case of CTs, optical CTs can be used, which is a newer emerging technology as well. So this particular case, all of that information is going into the merging unit, and the merging unit is using that sampled values protocol to share that information out on the network with either the relay, like breaker control relay. You could share CT information for bus relays this way because it's all networked together. Instead of changing multiple wires, say for CT wiring to a bus differential relay, you can reconfigure it on the configuration side and the setting side. So it's not lifting wires anymore, it's changing configuration, which is in large part where that savings comes from, because it's not rewiring, having to take out a screwdriver and move a wire from point A to point B. It's changing a configuration in the relay itself. So we're about to move on to the configuration settings documentation part of this. So our first example is just signal documentation. You know, what relay or what relays are putting out, what they are publishing, and what the point names are called. So this is just an example of what that might look like. Those of you that are familiar with SCADA point sheets, this looks very, very similar to that. Where is it coming from? What relay, the voltage level, if you would like to document that, what the signal is called, description, and what the status means. So Costa was talking about the data model a little bit earlier. This is another place where that can be documented, and this information can be used when the configuration and settings are happening, which we will get to next. So one of the big questions when I first started getting into 61850 is, okay, this is all very nice, but how does it actually happen? What does that look like compared to what we do now, where you might have a settings file that you push to a relay and you move hard wires around and that sort of thing. So this is a general overview of configuring 61850 subscribers and publishers. The configuration tools for Each major manufacturer differs slightly in the way that this is handled. However, this is a pretty good general overview. So for those of you that are not familiar with those configuration tools, this is the part where I'm going to name names. Schweitzer's version is called Architect. ABB relays are configured using PCM 600 and IET 600, and GE uses a software called Viewpoint Engineer in conjunction with its EnerVista configuration tool and settings tool. So these tools are a little bit different than the settings software I think we're all familiar with. However, they all work in much the same way. So typically the process is you create a new site or a new project. Costa was talking about the hierarchy of the SCL files, and that's SC as in Charlie, L files. So the site or project is typically called SCD, so even the file extension is SCD. And within that SCD, you have your individual IEDs that you add to that site or project. And when you do that, it creates a CID file for each one of those individual IEDs that holds this configuration information. After your IEDs are added to your site or project, you have to configure data sets. And these data sets are user configurable. There are some manufacturers that have standard data sets that they provide with the relay. Others allow you to do whatever you would like. Those that provide them still have the capability to do whatever you'd like, so that's not a restriction, but you have something to start from in some cases. So these data sets could be information for breaker failure, initiate and breaker failure tripping. You might send similar information within the same data set. Once you configure that data set, you set up the publish messages from the publisher relay using that data set. So you say, okay, I want to publish this data set out onto the network, and I want to make sure that it includes XYZ piece of information when it is published. After that, you move to the subscriber relay, and you are able to look at the list of published messages that have been configured for your particular site or project and choose which ones you want that relay to subscribe to. So again, in the case of a bus differential, you might have a breaker and a half, where you have several breakers that are all going to be a part of this bus differential. And you have each relay with the breaker closest to the rail publishing information about breaker failure initiate and maybe even breaker failure trip. And typically that is passed to the bus differential relay because it's already going to be tripping a lot of those relays or a lot of those breakers anyway. So that could be one way to group these published messages and to have your subscriber relay subscribe to that information. And at that point, after that message is subscribed to, you can use that variable, and the way this is handled differs slightly between manufacturers, but you can use that variable in the relay logic. So whether it's a piece of status information, it's an actual trip, it's that BFI that I keep bringing up, that information is used in relay logic. So this is the general overview of configuring 61850 subscribers and publishers. All the manufacturers I mentioned earlier have fantastic guides for how to do that within their individual platforms. So if you're curious, I'd be happy to send you some of that information. But in general, this is what the process looks like. So moving on to documentation. So how do we document that? I brought up your DC elementary or your DC schematics earlier, where at least as a design engineer, I'm very used to pulling out those DC schematics to see how something is going to function. With this type of thing, you don't have those DC schematics with the hardwired signals necessarily anymore. So I've seen a couple different ways to document goose message interaction. This is an example of how it could be shown on a drawing, say an AutoCAD drawing, where you have the goose signal name, the relays in boxes separated out by name, the local variable, or whatever you're calling it in, say, the publishing or subscribing relay. The publishing relays are bolded, and that's how you know that that is the publishing relay. And then the logic variable and where that's coming from, if you have a logic diagram to refer to, can be added as a drawing reference to this. So you can see at a glance what the signal name is, where it's coming from, where it's going to, and also have a reference to go back and look at the logic and dig more into more information about that signal. So this is one way that I've seen it documented. The second way I've seen it documented is in spreadsheet format. So you have a list of your publishing relay, the goose signal name, and then the relay here up at the top. So if you are a company or an entity that doesn't maybe necessarily use logic diagrams in DWG form, maybe you have those in Excel or some other format, this may be a good way for you to document the message interactions, so you can see how the publisher relay, so relay A, this signal, relay C is a subscriber to signals 1 and 5 in this case that are being published by relay A. So you can see this at a glance, exactly how they're going to interact with one another. So these are two ways that I have seen documentation of the interactions from relay to relay. So that is a very high level overview of implementation examples that we have. As I said before, there's many different ways to do this, and every company and every client that we have has their own preferences and ways to do things. So this is by no means an exhaustive list, but is a pretty good example depending on what you like to do in your company. So that being said, that is the end of our presentation part. So Del, are you ready to move on to the Q&A?
Oh yes, hello everyone, welcome back. We did get, well, first of all, thank you Brittany and Costa for your presentation. I did want to get into some of our questions. If, again, you do have a question from today's webinar, feel free to put it in that questions box, and we would love to tackle those right now over the next few minutes. If you have a question that maybe you would rather ask offline, you can do that. We have some, our contact information should be in the registration information that you received from GoToWebinar. You can send those our way, and we'd be more than happy to get with you there as well. So as some questions are coming in, I did want to say we did get a couple responses on why you may not have implemented communication-based protections and those obstacles. So Brittany and Costa, you may, I don't know if you'd like to respond to any of these, but one of those was communication-based protection may not happen because standards are driven by clients. Then another one is, where did the other one go? Option to implement communication-based protection is not available as a consultant with my clients. So some things about the standards driven by clients, the client doesn't either have a desire or standards in place at all. So maybe some client-based reasons there. Any comments on those types of situations?
Yeah, that is definitely something that I know I have seen, and is part of the reason why we wanted to put on this webinar, to show that you can take it slow, you can dip your toes into it and figure out bits and pieces as you go. It doesn't have to be the whole thing right off the bat. So definitely understand those restrictions in a consulting world, having been in the same shoes.
Yeah, I would like to add that the implementation of 61850 in North America didn't start that long ago. So slowly, the different utilities are starting to convert their substation or build new greenfield substation, which are 61850 enabled. So as time goes on, we will see more implementation of 61850 across the board.
Thank you. Thank you for those. Question from the audience. Please give some examples of the MU's available existing devices that perform the digitizing and or sampling.
Sure. So there are two variants that we know of that are available. GE, of course, has their brick, and Schweitzer has recently produced their TMU. So the TMU actually uses Schweitzer's tidal protocol. So for communications between the TMU and the relay, so it's a little bit different than the brick. But there are some industry examples that will digitize the signals to pass to a relay.
Any insight on your end, Costa?
No, I think I'm good with this
Okay,
one.
thank you, thank you. Next question. Is there any difference in service life of a 61850 installation versus traditional?
I do not think that it would vary very much from a traditional installation. These manufacturers that are creating the merging units and the relays that are being used in a 61850 station are the same manufacturers that we're using, to do traditional design. So I don't see a big difference in the service life. Other than when it comes time to upgrade certain components, as long as they're 61850 capable, and the capabilities of the IEDs across the board are within the standard, and there is some complexity to that. So I'll leave it at that, but there is some complexity to that because of the different additions of 61850 and evolutions of the standard. But the idea is you can take out a particular component and replace it with the same configuration, and it's a lot less effort than having to unwire and rewire, say, a new relay.
Yeah, and I would also like to add that during, after the configuration of 61850 in the substation, it involves part of it involves documentation of those configuration, and that will later on help in reducing the maintenance cost that is typically associated with fully hardwired substation. So in that sense, yeah, I mean 61850 might give you better service life than traditional hardwired substation.
Okay, thank you for those answers. There's still time. We still have a good time left to do Q&A. So if you have a question, get those in. Other question here though, and while we are still accepting other questions, let's see, here we go. Have you had clients who have taken the stepped approach to implementing 61850, and how did it go?
Yes, we have had clients that have taken a stepped approach. It was very similar to some of the first examples that I showed, where the communications between merging units and the relays were digitized and the hardwired communications were kept. I have seen that approach taken. I have also seen in instances where there is redundant protection, so a primary and a secondary system, or basically redundancy for NERC's sake. There has been a choice made to do traditional design, say for the primary, and utilizing 61850 for the secondary. So that way there's some comfort level that the primary will work even if there's an issue with the secondary. So I have seen it done in both ways.
Good, thanks for your answer. Thanks for your answer. Next question is, how many logical nodes can there be on a relay or IED?
Yeah, that's a good question. So there can be multiple logical nodes in a physical device like a relay IED. So those logical nodes, as I've talked in my presentation, those logical nodes can represent different power system functions that are being performed. Like for protection, if you have protection data, then the logical node that groups that protection data, you will have that protection logical node for that. Also, like if you're modeling, as I said, if you're modeling circuit breaker and handling the information for that circuit breaker in an IED, then you will have a logical node for that switchgear circuit breaker, which will start with the letter X and is known as XCBR according to the standard. So yeah, so you can have multiple logical nodes in a single IED, and that's how you can concentrate a lot of data within a single physical IED, and that can be accessed in the 61850 network.
Thank you, Kostab. Thank you. Next question, how easy or hard is it to troubleshoot problems during commissioning with no DC logic diagram?
So I've seen this done a couple ways. So the traditional way that I've seen is a couple different things. You have a DC schematic in order to do your wire tracing, to verify circuit continuity, to do the basic hardwiring test, and then you have the relay testing itself to test out the logic. For 61850, I've seen or had clients that will utilize the sequence of events recorder inside the relay to look at signal timing and also look at exactly what's happening in the relay during a testing scenario. So with the depictions of the interactions that should be happening that I showed earlier, whether that's a spreadsheet or the DWG, you can still do that tracing, except it's now all digital. It's not necessarily verifying a hardwired circuit.
Thank you, Brittany. Thank you for that. A few more questions we have here ready to go. Have you received any feedback from the field on their experience testing 61850 designs before putting them in service?
Yes, I have. In one case, it was actually a surprise to the field crew that showed up that day, which was rather interesting. But once we got through the concept of 61850 and what it was and went through the documentation with them, the feedback at the very end was actually that they liked it because it was a lot less labor intensive. Again, you're not moving around wires, you're not having to do certain circuit continuity testing. It's done digitally. So they actually came to really like the simplicity of commissioning with 61850.
Mm-hmm. Huh, that's very cool. Very cool to hear that. A couple more. Do manufacturers and OEMs provide templates for data models for their equipment, or does the implementer need to do that?
So my understanding is the data models are set by the standard, and Krista can probably chime in a little bit more there. But there are some manufacturers that will give the data set templates that I was talking about earlier. And Kostab, I don't know if you want to add more about, from the standard perspective, what that looks like, but that's been my perspective as far as, what type of templates are available.
Right. I mean, the data models and the data objects are standardized. So those come from the IEC 61850 standards. And as you were saying, manufacturers can, collect those data objects and put them in a template for the users to use. But yeah, the basic thing is the data objects or the data objects which are being mapped to the protocol and how and the method to do that. That's all there in the standard.
It kind of maybe possibly going along with that idea of guides, standards, can you recommend any publications or articles that are good guides to actually doing the work?
Yes, that was actually something that I mentioned earlier on in the presentation. Each manufacturer has some great guides to not only using the configuration tool, how to use that tool specifically, but also what does it look like if you implement a specific scheme. There is a manufacturer out there that has an example of how to do fast bus protection using 61850 and how to get that configured. So there are resources out there available from the manufacturers giving examples on how to do the implementation for certain schemes. So that information is definitely out there. And if you're curious about those, I can definitely point you in the right direction.
Great, thank you.
I would also like to add that the various software testing companies which does the IEC 61850 software, they also have good guides about 61850 theory and how the different configuration and different IDs are done. So there are lots of IEC 61850 software testing companies, and you can get those resources from the website.
Great, thank you, thank you. We have one more question, but before we go, if you did not submit a question, or maybe you are, the brain starts percolating and you get a question later on in the day, you can reply back to the registration emails, and that will come right to me if you have a question, and I'll make sure Kosov and Brittany get those questions, and we will do our best to get our answer to you in an efficient and timely manner. Before we start wrapping things up, the last question: any experience with retrofitting old substations?
I'm going to assume that we're talking about taking a substation that is existing today using a traditional design and converting it to 61850. And yes, we do have experience with that. There's a couple different things that I've seen some clients do in order to facilitate the cutovers from traditional equipment to 61850. In some cases, an interfacing relay that's 61850 compatible can be used as a temporary measure to interact between those devices that are using 61850 type communication with those that are not capable of doing so. So that's one thing that I've seen. The second thing that I've seen is, if you have a partial substation where the majority of the substation is being redone, in some cases you can have cutoff points, and normally that's done by voltage, where you have, say, like a transformer. You can use those transformer relays to kind of translate the 61850 messages from one voltage to hardwired on the other side of the transformer. So that's certainly a good transition point to look at when you are thinking about fitting older substation with 61850. So one is more temporary construction, how to do the cutovers, and one is for more longer term as you complete certain sections of the substation.
Okay, great. Thank you, Brittany. Okay, that is it for our Q&A time. Thank you everyone who submitted a question. And again, the Q&A doesn't need to end here. If questions do come up later on, again, you can always contact us and we will respond with the answer that we can find. So again, thank you for participating in that. Thank you for sending in your questions. So that wraps it up for us today with exploring IEC 61850. Thank you so much for attending. Again, be on the lookout for our future webinars. Our next one coming out in late spring about CHP. Also, if you attended today, in about an hour, you will be getting an email from GoToWebinar with a message from us linked to the recording of this video presentation, this webinar. Feel free to share that with anyone who you feel might find interest in it, or just keep it for yourself and you can watch it as many times as you like. Also, your information about the credit hour will be in that email as well. Anything else I'm forgetting? When you do log out of this webinar, you will be given an opportunity to take a quick survey. We'd love your feedback. We want to know how to make these even better. How can we take these to the next level? We'd love to hear your feedback. It really means a lot to us here at Commonwealth. With that said, on behalf of Kostab and Brittany and the Commonwealth team over here, we thank you so much. We're very thankful that you were able to come today, and we look forward to seeing you at a future webinar event. Find us on LinkedIn, and we'd love to see you there. Have a great day, everyone. So long.